So since we're running a bit short on time, let's go ahead and work through these. So this first one, find ourselves in the database. Well, we know we're going to do a match on a member node, and we can do a lookup by comparing the name property of this member node. So we'll say we're m.name contains. So we can do contains, or we could even do strict equality. Let's look myself up. So find Will Lyon and just return me. So here I am. We can see the groups I'm a member of, so I just double-clicked on those. So I'm a member of 3 groups in OSCON. Okay, so number 2, how many groups am I a member of? Well, we can do that visually, but we know the pattern we want to look for is where member is member of, I think is what we called it. Just member of? Yeah. Okay. So member of a group. And if we're just interested in a count, we can just return the count of G, and I get 3. So I'm a member of 3 groups. And what topics do these groups have? Okay, well that makes our traversal just a bit more complex. So we can say now, for the groups that I'm a member of, let's traverse out along this has topic relationship. And now let's return T. Now if I return T, let's look at this in row format. Okay, so I have Apache, open source, MySQL, MapReduce, Big Data, NoSQL, Apache Pig, Hive. Here's Big Data again. Here's open source again. So I have duplicates. So why is that? Well, this is defining sort of a path, right? So, so I'm going to start from the will node to the group node to a topic node. And that means that multiple groups are going to have the same topic, right? So I go through the graph database group. It has the topic open source. I go through the, I don't know, the Cassandra group. That's also going to have the topic open source. So if I just return T, I'm going to return sort of those duplicate topics that show up in multiple paths. But I can return just distinct nodes by just adding this distinct modifier. So now, so previously I had 36, now I have 28. So distinct to remove duplicates. And now which topic shows up the most? Well, we can return t.name along with a count of the number of paths that we found. Let's order by that count descending. And Big Data and NoSQL show up for all 3 groups that I'm a member of. Hadoop, Mongo, database development, and database professionals show up twice. Was anyone able to find themselves in the data? Yeah? Cool. Do your topics make sense for things you're interested in? Yeah? Okay. Cool. Okay, so now we've done that. We can now just extend our query just a little bit to now exclude groups that I'm a member of. So, so now all we do, if you remember our previous query was find the graph database Neo4j group, and then find groups that have the same topics, do a group by an account, and that's my recommendation. But now I need to exclude groups that I'm a member of. So I say where not exists, member is a member of the other group. So that's going to filter out any groups that I'm a member of already, because that's not a relevant recommendation. And I think my recommendations are still pretty much the same. Big data developers, Austin Graphs data processing algorithm, so I'm not a member of any of these groups, so they're still relevant recommendations. But we can now make this a bit more personal because, right, we said that even if you're not a member of the Graph Database Neo4j group, you're a member of some other groups. We want to see across all of the groups that you're a member of, and across all of those topics, like what other groups have those topics in common that you're not members of. Let's recommend those to you. So now we can, rather than just starting at the Graph Database group, we now start at the member, and we say, okay, find Will, find the groups that he's a member of, now find the topics of those groups and the groups that share those topics that he's not a member of, and again, the rest is pretty similar to the previous query, using the number of topics in common as a score for the recommendation. But now I get a bit different results. So now Big Data Austin becomes the most relevant recommendation for me, and some Hadoop group is up there as well. So this is where you're able to see if you're a member of, say, like hiking groups, and instead of these technology groups, you're going to start to see recommendations that are more relevant for you based on your interests. Okay, and we'll skip that so that we can take a look. Yeah, let's go ahead and do this next one. So the next piece here, so we said, okay, we can infer interests from groups that you're a member of, but we also have information that the user explicitly gave us here in this member CSV file. So we have this semicolon delimited list of topics that the user has said, I'm interested in these topics. So we want to make sure we can take that information into account, as well as what we're sort of inferring from the users by looking at the topics related to groups that they're a member of. And so this concept of factoring in information that the user has both given you explicitly, along with things that you're sort of inferring from their actions, I think is really an important thing to think about when you're building a recommender system. And actually, where this is really relevant is in online dating sites. Because when you fill out your profile, you're not necessarily talking about the real you, right? Like you're projecting perhaps who you want to appear as, right? And so a lot of the online dating sites that use graph databases, they need to make sure that they are actually not just sort of taking that as the only information for finding similarities, but also inferring information from the user's actions, right? So inferring things from your social networks, these kinds of things as well. So we want to make sure we can take that information into account. So we're going to extend our model just a little bit by creating this member interested in topic relationship now. But we need to just think of how we can work with this semicolon delimited list of topic IDs. We're going to talk briefly about a couple of new Cypher keywords, split and unwind. Split, this is very similar to split in lots of other languages. It splits a string into a list based on some delimiter, right? So if we have the string 1, 2, 3 separated by semicolons, and we split on that string with semicolon as a delimiter, we get a list of 1, 2, 3 as elements. And then unwind allows us essentially to iterate over each element in a list. So what we need to do is just combine these. So we need to unwind over the results of calling split on this list of topic IDs, which is what we're going to do right now. OK, so for this import, just going to start it running, and we'll look at it now. So what do? So we iterate over this members CSV file, and we split the topics, row.topics. We split now topics will become a list of topic IDs. So we can then unwind over them, which will then iterate over each of those topic IDs in that list, match on the member, match on the topic, and create this interested in relationship connecting the member and the topic. OK, so that ran. It created a couple 100,000 relationships. So now we can write a bit more complicated query. So this one's really interesting. Let's run it first, and then let's break it apart. So we run this, and we get back some recommendations. So we have some groups that were recommended. We have some list of topics, and then we have a score. And in this case, so my #1 recommendation is Next-Gen Native Hadoop Big Data Apex Users Group. A lot of buzzwords in there. With a score of 8. It's tied, I guess it's tied with a couple of others, but we'll just treat it as #1. So it has a score of 8, but there are only 3 topics in this list of topics that are, I'm sort of saying these are topics in common with those that I'm interested in. So how did we come up with this score of 8? Well, what we did is we essentially said, OK, for every topic that you said that you're interested in, how many groups are you a member of that actually have that topic? And then we sort of assign that count as a score for that topic, right? So this is sort of, again, this idea of combining information that you've explicitly given meetup.com with observing some of your behavior, right? So on your dating profile, you say, oh, I'm very interested in going to the gym. And here we're checking to see how many days a week you actually go to the gym. And we use that to sort of score that in your recommendation. And that's what we do here. So let's look at this query. So it starts off and it says, OK, let's find Will. Let's find the topics that he's interested in. And then let's find the groups that he's a member of that have these topics. And then group by member, group by topic. Members only has a cardinality of 1, so this ends up being group by topic. So for each topic, let's count the number of paths that we've brought into scope for that topic. So that's going to be the number of groups that I'm a member of for this topic that I've said that I'm interested in. And then score now becomes the sort of weight for that topic. And now I match on other groups that have this topic that I'm not a member of. And then when I return the other group as my recommendation, I collect the topics that I have in common, but then I also sum up the score for these across these topics. So now, so I think what I have here is 3, 3, and 2. So I think I have 3 groups that have big data, 3 that have open source, and 2 that have NoSQL, which gives me a score of 8 for those 3. So I'm now able to score my recommendation a bit more smartly, which I think is really cool. Questions on that? Yeah.
I'm having trouble thinking through the
this.
Because of the topic?
So your question is like, why is this comma here?
How does that work? Like, what do you call that operator in something other than a comma?
Yeah. So really, it's just a way of expressing a more like complex pattern, right? So it allows us to sort of combine this into one pattern, right? So member here is the same node here, right? And topic here is the same node here. So I don't know if there's a name for it, but it's just allowing us to express a more complex pattern that we're not able to write in one line because we have sort of this circular reference, right?
Is it a little bit like a subquery?
I wouldn't call it a subquery. No, I think of it as just a way, just a way for us to sort of express like a more complete graph pattern in one line. Yeah. Yeah, we should have some interesting academic sounding name for it.
So they're just implicitly anded together when you do that?
So really, like what goes on under the hood, so we can look at the explain for this. Explain is Cypher has to choose what we'll call the entry point, right? And so we have something that has a constraint and an index on it, so that seems like a good place to start. So really what we end up doing is like starting here, expand is like a traversal, and then we do another traversal, in this case from the topic, right? So we start from the member, we go to the topic, which is this, and then we go again from here, the topic now to the group, right? And so the sort of the order that we traverse it, again, is done by inspecting like the state of the database. So what indexes we have, the cardinality of the different labels and so on, right? So so the actual order that we traverse it is not going to be the same for every database.
If you had a clause there that didn't reference member and topic, it was just going to pull, like, if you graphed it, two completely unrelated sets onto the screen.
How do you mean?
So let's say for example, after the comma, you had a similar clause to the first one, only with a different name. So then you're going to get, and then you're returning, I don't know,
Oh, I see what you're saying. So this is like some other member, and this is like some other topic. And your question is like, what is that going to look like if I run that query?
Well, you probably need to change some of the rest of it, or drop the rest of it, and just return all the member and topic objects. Because I guess what I'm stuck on, I'm still just trying to understand it. The fact that the same member reference and topic reference were in the second clause is very impactful to the way it's interpreted. It's like intersecting two SQL queries because of that. So if they're not, then what is it?
Yeah, right. So it's really just shorthand. So if we go back to what I had before we So if we go back to this. So it's really just a shorthand for us to be able to express patterns that, because we're forced to project a graph, which is like this very connected thing, we're forced to project that onto one line of ASCII art. We can't like draw that on a line. So that comma and sort of allowing us to do like disjointed but not really disjointed patterns, like really what it's doing, like it's similar to, so topic, there's some group over here, right? And I have this group, and I want to express the fact that that now, so that's almost this, but now I want to express the fact that this guy, this member, now goes here, right? This, if this was valid, this is essentially just what I had, but on 2 lines with a comma, right? But this isn't valid because it's not clear where my entry point for binding member is at this point, right? So it's just some shorthand that allows us to draw that, basically.
So will it only work if it is something that's ultimately all the way connected and not 2 separate paths ending in separate places?
No, I mean I can have like disjointed things that I'm looking at, but then because of the nature of Cypher, like every path that I end up traversing gets piped through to the next. So if we look at sort of this form of a Cypher query, right, is we do some operation, we have some paths, we pass that on to the next operation. If the things that I'm looking at are disjoint, then that introduces the concept of a Cartesian product, and it means for like every row in this thing that I'm looking at, I have to do the same operation for all pairs of those in this other disjoint thing. So in general, we don't want to have queries that have Cartesian products. Yeah, good questions. There's another one over here, maybe? Yeah.
So you couldn't put, where you have the second member, you could just make it equal to the line as well, where you still have the same problem?
Let's try it. I don't think it's going to work like this. Oh, it actually did work like that. Yeah, so that does work. So maybe Cypher has gotten smarter than me. Yeah, so that does work. It's just sort of more readable. Yeah. Cool. Okay, so we have about 30 minutes left. Let's see what we haven't covered yet. So we did sort of inferred interests. Let's really quickly run through this event import, and then I want to at least go through sort of this example using the Python driver and then some of the sort of data science-y Python stuff. So let's really quickly just look at sort of the type of data now that we have for events. So groups host an event, members RSVP to an event. So we have the kind of information you would expect for an event, like name, description, it's at some venue, just like all of our other nodes, we have an ID that uniquely identifies the member, or sorry, the event. So we're going to create a constraint on event ID, and we'll create an index on time, which is going to be the timestamp. So this is what our new data model is going to look like. So group is going to group hosted an event, and eventually we would extend venue and RSVPs and so on. But for now, let's just create our event nodes. So this is really similar to the other imports that we did, where we merge on event with an ID to avoid creating duplicates. We have about 4,000 events. We can look at a few just to make sure we imported those correctly. Yep, looks good. Okay, and now we need to connect events to their groups. So that query I ran really fast was now iterating through that event CSV again. Let's match on the group, match on the event, and now create this group hosted event relationship. So we ran that. And now let's look for all groups that start with graph that are hosting, that have hosted an event, right? So some event that occurred previous to now. And we can see, okay, here's Graph Database Austin. It had some groups, such as building killer apps on Neo4j 2.0. That's an old one, and so on. Cool. So that's the data model that we wanted. And then we can do some more things with sort of a simple recommendation being to show me future events for my groups. And one thing that's really important is this idea of layered recommendations, which is this idea that we have different sort of scoring components in a query. So we saw previously where we were calculating a score for topic based on the number of groups that you're actually a member of for that topic that you said that you were interested in, right? So that might be one component of a score for a layered recommendation. But then we might have other components for that, such as like its distance to where you work, a number of like your friends that are there, some similarity score that we've calculated based on, I don't know, you and topics we've extracted from the abstract, things like that, where we're doing sort of some weighted average. And so that's what this gets into next. I'm going to skip that because I want to talk a little bit about sort of what we can do with the Python driver for Neo4j and see if we can extend the data that we have on events a little bit. So this is a Jupyter notebook. It's on GitHub. The link is in the slides, and I'm just going to go through it kind of quickly in the time we have left to get sort of some of these concepts across. But basically, what we're going to do is connect to Neo4j running on AWS from Python. And to do this, we need to grab the username, password, host, and these kind of things from our sandbox instance, which we can get here in the details tab. So here's my IP address for this one. If you were running this locally, it would just be, localhost or something like that. I need my password. And finally, the HTTP port for this one. Okay, so we'll run that. So we're going to import Py2Neo. Py2Neo is one of the Python drivers for Neo4j. There are a few others. There's another one that's actually a Neo4j official driver. Py2Neo is based on that, but has some added features. For example, you can pass a result cursor from Py2Neo directly into the constructor for a pandas data frame, for example, right? So just some convenience things like that. So we create this connection to Py2Neo, and then let's run just sort of a sanity check here. So match on all nodes and return the count. And as long as no one went into my Neo4j instance, since I have my password up here and deleted everything, we should get back, 37,000, cool. So thank you for not deleting my stuff. There's still time, I guess, yeah. Okay, so we did all this stuff. This is sort of the import stuff, importing events, RSVPs, which we haven't done yet, but let's look at some keyword extraction stuff. So there are lots of sort of text processing NLP libraries in Python for working with text. Text blob is one of them. Does anyone use text blob? A few folks. So there are lots of different things. There's another one that uses an algorithm called text rank, which I actually like to use because it uses a graph algorithm. Basically what it does is it takes some text and models it as an adjacency graph. So every word that appears next to a word has a relationship to it. Then it runs PageRank on that graph. And if you want to get the top in keywords, just get the ones with the highest PageRank. And the thing I like about that is there's no training involved for a text corpus. And it ends up working out okay for smaller text. So for things like the description of an event, that's nice. But TextBlob is good too. It has some things like sentiment as well. Okay, so we're going to import TextBlob. And then let's look at just one simple example. So let's match on an event where the event has a description that's not null. And then we calculate some random number and do a limit one, just to get some description text at random. And because we're using rand in there, we get a different one every time. So this is the description text for some event, and notice that it's HTML, right? So we see a paragraph tag and so on. So here's just something that I grabbed from Stack Overflow to help us remove HTML from Python, or from our text here. And then the next thing we're going to do here is get a TextBlob object after we strip out the HTML from that text. And then we'll look at both sentiment, and then I call it keyword extraction, but it's really noun phrases. And what we get here for our noun phrases or keywords, some of these make sense, some don't. So hey coders is the first one. Ruby is another one. Study group. Elasticsearch is in there. So you can see some of these things, if our goal here is to figure out what this event is about based on the text, like this is okay. This is some sort of Ruby study group for coders. Okay. Now, if we think of beyond just this one, let's try another one. See if we can. Here, this one's much shorter. And what do we get? Map time, ATX, pizza, rack space. So, yeah. Anyway, what we want to do is sort of extend our data model a bit. So we know that we have topics for the group, but we don't have topics for the event. So if we were to factor in information about the events that a member has RSVP'd to, we can then infer, right, so along here, we can then infer their interests in these keywords as well to make more relevant recommendations. So that's what we want to do, is we want to now write back keyword nodes to extend our data model from the event. So we'll create a constraint on keyword using the name property. This is just a function that takes a Cypher query and runs it, and then it assumes that it's returning events with an ID and a description, runs that description text through TextBlob, gets an array of the keywords, and then this piece is writing them back to Neo4j. So it's iterating over this array of keywords, creating a keyword node, connecting those to the event. So we can then just say, find all events for graph database Austin, pass that query into this AdWords or add keywords. So each one of these objects are all the keywords we found for some event. So this one, the keywords are Neo, Kevin Van Gundy, who's one of my coworkers, Austin, Neo4j, training course, meetup, intro, graph, introductory session. Okay, so this is an introductory training course for graph databases in Austin. Okay, that one makes sense, right? And so we can see, again, we have graph database, and a lot of these. So we can see, okay, well, if we go back to Neo4j, which is here, started a keyword, started intro. Okay, so these two events share this keyword. Okay, so that helps us give some information about finding relevant groups, relevant events. But we ran it, of course, on just one, all the events of one group. So that's not as useful. So let's run it over lots and lots of different groups. So we ran it over 100 events. Let's do 100 more. And now when we come back, we can see, okay, so here are all of the events that have the intro or introductory keyword. So we can now factor that information into account to say, okay, if you're sort of introductory level, these might be good for you. Although I don't know how good this is because the first word of these two events is advanced machine learning. So either someone didn't write a very good abstract or something's wrong with our keyword extraction. Anyway, okay, so that's one way that we can apply some sort of NLP stuff to Neo. To graph databases. I want to talk now, though, about this idea of community detection or clustering. So when we said towards the beginning of this, we were talking about content-based approaches for recommendations, and we said, well, if we have a product catalog and we know that these books are in these categories and we can find similar books that are in the same category, that works great if we have that information sort of already available to us. But can we infer that kind of stuff? Like, can we infer these sorts of clusters if we don't have that explicit type of catalog information? And so one way we can do that is by using clustering or community detection algorithms to sort of examine our data and then infer where there are clusters of similarity. So we can use the iGraph package in Python, which is this is a port of the iGraph package in R. Has anyone used iGraph in either Python or R? No? A couple of people? Okay. So what we want to do now is build a topic co-occurrence graph, right? So we want to know where topics occur with another topic. We want to know how many times they occur together. And then in iGraph, we're going to run a clustering algorithm on that topic co-occurrence graph to find clusters of topics. So then when we know that, say, you're interested in NoSQL as a topic, we can then find similar topics that you might be interested in, even though there may not be groups that you're a member of that share those topics, if that makes sense. So the first thing we need to do is figure out how to build this topic co-occurrence graph. So what we want to do is for every pair of topics that occur together, and by that I mean for a pair of topics that are connected to the same group at least once, I want to know across all groups how many times do those topics show up together. So this is the traversal we want to do is for all pairs of topics, so this topic and this topic that are connected by a group. So we don't specify it, but we know this is going to be a group in the middle. We then do a group by that pair of topics, and we're specifying the ordering of the IDs here, so we only get sort of unique pairs. then just count the paths, and that's our weight. And so this is the result that we get. So open source and software development show up together 55 times. Open source and computer programming show up together 50 times. So we have this sort of list of topic pairs with their weight. We can then actually just pass the result of that query to the constructor for iGraph that gives us an iGraph object. So iGraph is now this in-memory projected graph of this topic co-occurrence graph that we extracted from our meetup data. And we can run really easily this walk trap algorithm. This is an iterative algorithm for finding clusters. Basically what it does is seeks to minimize what's called modularity. So modularity is the ratio of relationships that go outside a cluster to relationships within a cluster. So it starts off by saying, okay, every node is in its own cluster. Iterate, what does modularity look like? Iterate until it comes to some stable state. Where are we? Here we go. Okay, and so we have 21 clusters. We can sort of inspect what this looks like. So basically, it gives a group to every topic. So assigns, in this case, an integer to every topic. So in this case, MicroStrategy best practices and MicroStrategy mobile applications both belong to cluster 0. That sounds on point. Computer programming, learn programming, open source. Now, these 3 belong to a different cluster, which is labeled cluster 1. So now what we want to do is write these back to the graph. We'll add a cluster node for connecting each topic that belongs to a cluster. So now, if you can think of how this is going to benefit us, is when we say in that recommendation query where we said, okay, find the topics of the groups that I'm a member of, what are other groups that have those topics? Well, now we can write a more complex traversal that says, okay, what are the groups that I'm a member of? What are the topics of those groups? What are similar topics of those by traversing through the cluster node for those topics? Now find groups that have those similar topics, right? That's where we want to go. So this query will basically iterate through our clusters and will create a cluster based on that ID, right? So 0, 1, some integer value, and then connect each topic to the cluster node that it belongs to. So if we go back to Neo4j, just picking one at random, here's cluster 13, which has the topics inventor, inventors and product developers, intellectual property rights, patent, so IP kind of stuff. This is a big JavaScript, web development node, so sort of like web development stuff. Let's find one more just to sort of check how we did. So this one, cluster 4, come on. Cluster 4 is a lot of Salesforce stuff. So Salesforce training, Salesforce chatter, CRM, Heroku's in there, so maybe not perfect. But anyway, you get the idea. Cool, so that's how we can use clustering algorithms to help improve some of the information that we have available, right? So we don't always have, this sort of hierarchical product catalog information available to us. So we're about out of time. All the material is available in Neo4j Sandbox, so feel free to work through those. I just want to point out, since we talked a lot about recommendations, There is a sandbox use case in Neo4j Sandbox focused on recommendations. It has, so this one here, it has information from Movie Lens on movie ratings, and then also information from the Open Movie Database about movies and TV shows. And it goes through, I think, a bit more like data science-y type approach than what we did today, showing how we can calculate some of these like similarity metrics using like Pearson correlation, which is really good when we have ratings and that kind of information as well. So if you're interested in that approach, definitely check that out as well. Also, I would encourage you to play around with any of the sandbox instances. This is something my team built out over the last month or so, just sort of a fun way to share data sets. Cool. So we'll stop there. It's about 5 o'clock. Thanks everyone for coming. I'm here, all week. So if anyone wants to chat, feel free to message me. Twitter is probably the best way to get a hold of me. We'll leave this up. Cool. Thanks everyone. Cheers.